Okay. Uh, I'm talking about testing the incorporation of portable infrared imaging for future human missions. And in particular, I'm going to focus on the second year of fieldwork conducted by the RISE team. This happened last month, June of 2015. The motivation for this work comes from the goal to send humans beyond low Earth orbit onto a planetary surface. And when the astronauts go on to another planetary surface to work, they want to collect samples. And they want to collect efficiently and effectively. For that purpose, rapid in situ analysis of rocks and soils hold great science potential. This type of analysis is beneficial for some aspects of science, such as ensuring that the best quality samples are returned to the labs for more analysis. There are some candidate prototype instruments that will do rapid in situ analysis, and we have to test them here on Earth first. As for me, I test one of these candidate instruments, the portable infrared multispectral imager. The final or the ultimate goal of my project is to assess if this imager is really useful or not. But today I'm not going to answer that question because I'll take more time and work, but rather I want to talk about the process of image acquisition, the process of data calibration, and some issues that go with them. So this portable multispectral imager, how does it get used? I think it will fit into a sampling workflow, something like this one shown here. Before I get to any details, though, I want to make a note that we're not doing on-the-fly processing. So the instrument products will get used after the sampling. And this sampling workflow is testing the instrument strategy or the concept of using the instrument using our currently available resources. There could be other sampling workflows as well and strategies, and I think more will become available in the future once technology advances. But for now and our purposes, this is what we use with our limited conditions. So when the astronaut crew approaches an area of interest, first they scan the image or the scene using our imager. They get the multispectral images and then go out to collect samples. After sample collection, they look back at the images and then determine the representativeness of the samples that they have collected. And then next, they identify any potential areas of interest that they have not sampled yet. They will remember these places for future in case the site can be revisited. And then finally, they will document the spatial or relationship between compositional units. Now this workflow we tested here on Earth, we went to Hawaii, specifically December 1974 flow in Kilauea volcano. This is a good analog site for the moon or some differentiated asteroids. And this square shows the December 1974 flow. And then over here we test this instrument, multispectral imager. It has two main components. One is a thermal imaging camera. This is commercially available by FLIR. Another part are filters. These filters are designed to transmit at wavelengths shown here between 8.3 and 11.3 microns. This covers the atmospheric window. Now this instrument extracts useful information using emission spectroscopy. Basically, the sensor detects light coming from the scene, which objects in the scene are emitting light depending on black body radiation and emissivity, as well as downwelling radiance coming down from the sky and reflecting from the objects. Here we want to extract emissivity, which is an intrinsic property unique to different materials, and we take emissivity at multiple wavelengths, constructing emissivity spectrum. And emissivity spectrum will be useful for mineralogical analysis. Now, knowing the theory, we go out to the field and take images. First thing we do when we go out is to set up calibration targets. There are 3 targets, and 2 of them are black body targets. These are just square tiles with cavities, like the zoomed out image shown here. The cavities create the black body effect, and we have 2 of these at different temperatures. The third calibration target is a box with aluminum foil, which accounts for the downwelling radiance. Now, after having set up the calibration targets, we can put the camera onto the tripod and then the filters onto the camera and finally take images. So after all the image collection, we can move on to data processing. Like I said, we want to extract emissivity spectra. Here I'm showing one of the sampling locations from the December 1974 flow. This is in visible light, so what we can see with our eyes. And this one is the processed image. This image has been decoration stretched to show compositional differences in the scene. I also plotted some emissivity spectra for representative units. I chose 3 of them. First one, the green circle, is Pahoehoe basalt with some silica coatings. The diamond is a consolidated ash. And then the triangle is soil. So here you can see that the spectra are different for the 3 units, meaning that the instrument is capable of detecting compositional differences. So in the scene, we go out and collect samples. And we take the samples to laboratory and then take emissivity spectra again in the lab setting. We want to compare lab and field emissivity spectra to validate our instrument and our calibration techniques if they are working correctly and properly. Here I'm showing the comparison of lab and field spectra for 2 of the example locations in our field site. You can see that the lab and field emissivity spectra are not matching exactly one another, but they come close. And especially the spectral shapes, they are consistent. The band depth or the magnitude can be dissimilar, and that might be caused by environmental effects such as viewing angle or cloud cover. Now, arriving at these results, we have encountered some issues. One of the issues was finding a good optimal field of view. Generally, when we take images, we want to get close to the target to get good spatial resolution. But when the crew members are looking for samples, they like to move around, searching for the best sample to collect. So when that happens, they cover a wider area than what we expect. So finding a good balance between going close to get good spatial resolution and then backing up to cover a wider field of view was something that we did not expect beforehand and trickier than what we expected. So on the top is one example location, also decoration stretched to show compositional differences. This one is closer. And then on the bottom is another location that when the targets are farther away. Another issue was the location, or knowing the location of sampling. This is crucial when we want to compare field to lab emissivity spectra. In the images that we take, we want to know where the samples are coming from so that we can do a fair comparison between lab and field. Our first attempt in 2014, we did not think about this and had a very hard time trying to match or compare lab and field spectra. This year, we learned our lessons and placed sampling markers. This was just aluminum foil, and this was much improvement. Yet, we are still looking for something better method than just using old-fashioned aluminum foil. So to conclude from our second year of field work, we obtained better experience in using this multispectral instrument. And in particular, we improved data acquisition methods. We have improved data calibration or processing techniques. And also we have improved understanding of the instrument's role in the sampling workflow. And something that we had to keep in mind are environmental conditions in order to get the best quality samples. So for example, we want to get the best signal to noise ratio. that will come from warmer rocks as opposed to colder rocks, which depends on things like time of day or cloud cover. And then finally, assessing the ultimate usefulness of this instrument, multispectral imager, will require more field testing and more time. And that's what we'll do for the next 3 years. Acknowledgements. Thank you very much to my advisors, Deanne Rogers and Tim Glotch, and field leaders, Jake Bleacher and Kelsey Young. And many thanks to the RISE Team 2 members. That's the end. Thank you for your attention.
We have time for some questions.
Really, how much effect does atmospheric water and stuff have on the quality of your samples? Does it? Have you noticed clear skies giving you much a different spectra than?
Right. Yeah, it actually has a lot of effect. On a cloudy day or some rainy day, the spectra look the same for any kind of rocks. So that means what? Usually that's when the temperatures are colder and the signal to noise ratio is bad, and we're just picking up the noise part. So we really want to get the best conditions as possible.
Are you able to ignore the water effect, water spectra? Or is it washed out after hitting the rocks?
Yes and no. We usually take out the water effects, but in the very good conditions, we don't have to do that though.